So we've got Lab 2 was due over the weekend. Was there any issues with that? Any questions, any problems? Seemed like it went pretty smoothly. We also had a quiz that was due. I'll go over that today. I don't have a new quiz for this week. I'll have one for next week. But I do have Lab 3, which I'll assign today, and you can start working on it whenever. So the link to Lab 3's description is on Dropbox there. And there's the skeleton. Again, there's a tar GZ file that you can download to start from. And then there's the submission box. Okay, so quiz 2. Sure. 13th is the Friday that we know. Yep. Yeah, sometimes I have Friday and sometimes I put Sunday, but either way it doesn't matter because there's no late penalty for the weekend. So yeah, 13th, you're right, is yeah, Friday. But if you, 13th. Right, yeah. If you submit it though by, Sunday night, that'll work. Okay, so the first quiz question was a little confusing. This was something I came up with last year, I think, and I forgot to fix it. The question is, it gives a SystemVerilog module and asks what's not a problem. And it turns out there's multiple answers that work for this. So C is double driven. That actually is a legit problem because you've got an assign statement assigning C and then this always assigning C. So that is a problem. No sensitivity list for the always statement. Well, it doesn't have a sensitivity list because it's an always comb. You can't actually specify a sensitivity list for the always comb. So that's not a problem. That's okay. Cannot use if statement in SystemVerilog. Well, this one's a little confusing. Normally, you can't use it unless it's in an always. But in this case, it is in an always, so it's fine. So that's not a problem. Use of a blocking assignment in an always statement, that is a blocking state. That's a blocking assignment statement, and that's fine. In fact, that's correctly used because that's a combinational always, and in combinational logic, you should use a blocking assignment. So that's just a regular, just equals sign. That's not a problem. Cannot combine always com and assign statements in one module. That's fine too. It's no problem. And the always block has no default assignment for C. That is a problem because this will actually, this code will fail to compile because you've declared that always as a combinational logic, but there's no way that it can behave as combinational logic because if B is false, so if B is, like for example, if B is a single bit and it's a 0, or I assume if it's like an X or a Z. I'm not sure how that works if it's X or Z. But basically, if this if statement, if the condition on this if statement is evaluated to false, then C will not, there'll be no execution path through this always that'll assign C. And so normally that would become a latch. If it were just an always statement, it would become a latch, because C would have to retain its previous state, its previous value. And because it would be a latch as opposed to a flip-flop, because there's no clock edge defined, B would essentially become the clock, right? But it would be a level-sensitive clock like a latch. But in this case, you'll get an error because the compiler will assume that you made a mistake by not having an assignment for C through every execution path through the always. Does that make sense? You guys, is that clear? So one way to do that is just have a default assignment for C. But if you did that, you'd have to have a begin and end on that always too, right? Because then you'd have two statements in there. Okay, so if you had answered B, C, D, or E, that you should have got that one correct. Second question is, consider the Verilog module shown below. How many input signals are specified? That's pretty easy. It's looks like clock, reset, load, and seed. Clock, reset, and load are all single bit, and seed is 8 bits. So that's 4, right? Question 3, consider another Verilog module. Assume the module is reset with a reset pulse at the start of execution. What is the value of state in the first 3 cycles after the reset pulse? Okay, this one's a little trickier. So when we reset, Well, first of all, you've got an always FF that will respond to a positive edge on clock or reset. That means reset is asynchronous. You can reset this thing without a clock edge. And when you do reset, the state will become 1, 0, 0. If reset is low and you get a clock edge, then you will change the state. So you'll start at 1, 0, 0, and then on the next clock, state 2 will become 0. State 1 will become whatever was in state 2. So basically, state 2's value will shift down into state 1. Right? So in the first cycle, that state 2, which is going to be a 1, right? Because you read these numbers from left to right is most significant to least significant. So state 2 starts out as 1, and after the first clock, that 1 will migrate down to bit 1. Right? And then in every cycle after that, until you have another reset, state 2 and 1 will both be 0. Does that make sense? Because you're hard coding, state 2 will always get a 0, and state 1 will get the old version of state 2. Right? And then state 0 is state 1 or state 0. So see, I think, yeah. So cycle 0, you have a 1, 0, 0. Cycle 1, you got a, like I said, state 2 becomes 0, state 1 becomes the old state 2, so that gets a 1. And then state 0, you want to be able to look at, when you're evaluating state 0, look at the previous value of state 1 and 0, which would have been a 0, 0, right? So every time you're coming up with the next state, when you're filling in cycle 1, for instance, you got to look back at cycle 0 for your inputs. You want to look at the previous values for the inputs. So the value of the state in cycle 1 is 0, 1, 0. And there it is, 0, 1, 0. Okay, then in cycle 2, state 2 is going to be 0. State 1 is going to be the old state 2, which was 0 in the previous cycle. State 1, you're going to look at 1 or 0. So you're going to get a 1, so 0, 0, 1. So that's the evolution of this. You start out with 1, 0, 0, 0, 1, 0, and 0, 0, 1. Does that make sense? I'm not sure if I explained that very well, but the point is that when you're calculating the next state, look at the previous state, right? So in these always statements that are sensitive to the positive clock, you're always looking, it's using the previous value, the previous cycle's value to calculate the next cycle, right? Okay, question 4, give the value of signal A in the first 3 clock cycles after reset. This is a similar one. So we start out as 1, 0, 1 on a reset, and then you're going to take A and shift it 1 bit to the left, and then you are going to do an exclusive OR with 1, 1, 1, which will flip all the bits. Okay, but notice here that the first assignment statement is a blocking, and the second one is non-blocking. So because of that, the second line of code, you can take this sub-expression and substitute it in for A, because that blocking assignment will affect any subsequent lines of code in the always statement that use the outputs of the blocking assignment, right? So basically, what this is doing is it's shifting A by 1 bit and then flipping all the bits. Okay, so if you start out with 1, 0, 1, you shift 1 bit to the left, which will give you 0, 1, 0, and then you flip the bits, which gets you back to 1, 0, 1. So basically, this will always be 1, 0, 1. It'll just keep setting itself to 1, 0, 1 every cycle, right? Yeah. Does that make sense?
What if the first one was not blocking as well?
If that were the case, then only the second one would matter. So that would invalidate the first line of code. That's a good question. Yeah. Yeah, so if the first assignment was non-blocking, then it wouldn't have had any effect on this at all. Like it would have just been overruled, overwritten by the second statement. Because you can, again, just to clarify, you can assign a value multiple times in an always, but the only one that counts is the one that happens last, right? Okay, so what's the problem with the following code? This one is a combinational logic, but it's got a cycle in it, right? Because A is an input and an output in the same always. So you end up with a feedback connection, and that's not valid combinational logic, so the compiler will flag this as an error. So the options were always statement should be combinational but has a cycle, so that's the answer. Missing sensitivity list, that's not a problem. Cannot use addition and always com statement. No, that's true. That's not, you can. So that's not the answer. And use of blocking statement is not the issue. It's A. Okay, consider the following test bench. What function does some module perform? So from this, you have to infer what's going on in the design under test from the way it's being tested. So the way it's being tested is that you're putting inputs and you have an expected output. So basically, the test bench has a truth table in it. You're setting the inputs and you have the expected output. Make sense? So there's two inputs, I think just A and B, and one output C. And it looks like that is going to be an AND gate, right? Because if A is 1 and B is 1, the expected output is 1. But if there's any zeros in the inputs, then the output is 0, right? So that's an AND gate. Now, one thing that may not be obvious here is notice how I set A and B at the top, but I only set A here. That's because it's going to retain the old value of B, right? So this is test case 1, 1. This one's going to be 0, 1, right? Where A is 0, because B is still going to be 1, right? And this will be 0, 0. And then this will be 1, 0, right? So it looks like that's supposed to be an AND gate. Yeah, AND gate. Right. Okay, what are the first three values of A generated from the snippet below? So this one is just another sequential logic question. So we reset with 1, 0, 1, 0, 1. And then the next state of A is going to be a combination of bits that were in the previous state of A. And so the only way to really do this is, well, the only way I know of is just build a table like this. So when you get to cycle 1, you're going to fill in, each bit you can read from left to right. So the first bit is the old A0. So what that means is that bit, the old A0, is going to migrate down to here, right? So the old A0 is going to migrate down to the new A4, right? And then you got 2 copies of A1. So A1 is 0, so that you're going to put 2 copies of that right there, right? And then the complement of A3, which was 0, now will become 1, so that goes from 0 to 1. And bit 2 XOR bit 4. Bit 2 XOR bit 4, that's 1 XOR 1, that's 0. So that becomes 0, right? Make sense? Okay. All right, that's it. Any questions? All right. So our next topic is we're going to start getting into the RISC-V microarchitecture. So we talked about architecture, that's the assembly language, how you program it. That's the public part of a processor. And now we're going to talk about the secret part of a processor, the microarchitecture. This is the part that no company will ever tell you how the microarchitecture works. This is the trade secret part. This is the under the hood part. Okay, so before we talk about that, let's talk a little bit more about RAMs. So we've covered flip-flops. So let me clarify a few things here. So when I say register, sometimes I'll say register. Sometimes I'll say flip-flop when you have like an always underscore FF. So a register is like a multi-bit flip-flop, or that's one type of register, right? And then there's the architectural register that you have in the register file. Why are they both called register? I don't know, it's confusing, right? What's the difference? In the register file, you have a set of registers, and you can access one of those registers per port, and each port has an address. So basically it's addressed. It's an array. It's like an array where you can access, like typically with, I don't know if you guys remember from 212, but MIPS and RISC-V are 3 address architectures, meaning that instructions can have up to 3 registers in them, right? So the register file has 3 ports, which meaning that you can read 2 registers and write 1 register in the same clock cycle, right? So basically you can access 3 registers per cycle in a register file, but there's 32 registers in there, right? So what that means is you can't access them all. There's no reset, by the way. You can't reset a register file, but you can write one at a time. So you could reset it if you're willing to walk through it, 32 cycles and write each one to 0, right, over the course of 32 cycles. But the point is that you can only access 1 register at a time. The reason, or actually 3, because there's 3 ports, right? One per port, right? So what's my point? My point is that the register file is actually a RAM. A RAM is a memory array that has an address where you can access an element out of that array per cycle, per port, right? So for instance, here's an example of a RAM array. It's 1,024 words by 32 bits. So the first number is the depth. There's 1,024 addresses, entries, elements, locations. 1,024 entries. Entries in the RAM. There's 1,024 addressable locations in the RAM. That's the depth. And then 32 bits is the width, right? So in total, the number of bits is you have to multiply. There's 32 kilobits in there, right? Notice that the depth comes first, the width comes second. That makes sense, right? It seems like that's the same order that C uses, right? Row, column, right? Linear algebra is row, column. Row is first, column second. Depth is first, width is second, right? Right? And this has 1 port, and the way it's set up is there's an address input. Well, actually, I don't know how this is set up. I guess the address is an input, although there's no arrow there. So this figure came from the book, I think, a little unclear. So the address is an input. And then the data is shown as an input or an output. So it looks like we have the ability to write or read an entry in that RAM array. Now, in order for that to happen, we need some control lines here, like the read and write control line, which aren't being shown there. Okay, so yeah, I just got done saying that. So a memory array, a RAM, is 2 dimensions. There's bit cells inside the array physically. But when you use it, you think of it as having a depth and a width. So the width is the number of bits that you access at a time. The depth is the number of entries in there, and you can access 1 entry per port, right? So here's another example. If you have, this one is a 4 by 3-bit array, which has 12 bits in it. So that you can access 1 of 4 entries. There's 3 bits per entry. If we go back to this first example, this one, because there's 1,024 locations, in order to figure out how many address lines you need, you have to take the log base 2 of the number of locations. So if there's 1,024 locations, the log base 2 of that is 10, so there's 10 address bits. So there's 10 address bits and 32 data bits, because 32 is the width, right? Okay. Okay, so how do you build a RAM in Verilog? Is there a special way to do it? Kind of. So in Verilog, if you want to make a RAM, you have to describe the behavior of a RAM using the SystemVerilog semantics language. So, and there's different ways you can do it. So here's an example. So first I'm going to declare my RAM array using this really strange way of doing it, where it's still a type logic, and you still put the width first, as you would if you didn't have a RAM array, if you just had like a regular signal, multi-bit signal. So this is declaring a 32-bit wide RAM array, right? But then you add an additional set of indexes here at the end that define the depth. In this case, 8191:0 means that there's 8K entries 8,192 entries, and each entry is 32 bits. The reason I'm emphasizing this is that you'll notice that the order of these indices is now reversed. Because now we have the width first and the depth second. That's different from linear algebra, that's different from C and Python and Java. It's even different from the way people talk about RAMs when they say 8K by 32 RAM. Like if you open up your computer and just look at the RAM chips, they'll have that nomenclature where they have the depth and the width, right? They'll say, I don't know, 8 mega by 32, which means 8 million deep, 32 wide. So the actual chips inside your computer will say depth, width, but SystemVerilog, for whatever reason, does width, depth when you declare it. Only when you declare it, though. That's the way you declare it. So just try not to get confused by that. It's even more confusing because in the RISC register file, that has a 32 entry deep, 32 bits wide. So they're both 32. So that's called a 32 by 32 RAM, the one that's in the CPU. So, you look at that and it's, because it's a square kind of shape to it. Okay, so how many address bits do I need for an 8192 deep? Well, the log base 2 of 8,192 is 13. So I need a 13-bit address. So I'm going to declare an address. And I'm going to have a read data and a write data that'll also be 30, well, not also, but will be 32 bits because that's the width of the RAM. Now, from this, you can kind of tell how many ports do I have here. Well, I only have one port because there's only one address. But I do have data going each ways, in and out, right? So it looks like from this, I'm going to have one port, but that port allows me to read or write, or maybe read and write at the same time, right? So we have to read on to see how it works. So then I have this single bit write enable and clock. Then you can put an initial statement. This is optional, but you can list an initial, and in the initial, and there's no begin and end here because there's just one statement in this initial block. Read memh mem.txt mem. So this will initialize the memory based on the contents of that text file. Now you might say, wait, hold on. Obviously that's non-synthesizable code, right? Because if you're converting this to hardware, how's a circuit in hardware going to read a file? Well, it turns out that actually that is synthesizable. You wouldn't think it is. The reason is because the synthesizer, when it generates the RAM for the FPGA, it will generate the code on the design on the FPGA in a way that that RAM will be initialized with the contents of that file. But that only works on an FPGA, not on an ASIC. The reason it works on the FPGA is when you configure an FPGA, when you shift all the bits in to configure all the little programmable gates and the logic and all that stuff, part of that configuration is the RAM contents. So when you use the JTAG protocol, which is a bit big shift register, bit for bit shift serial, one bit at a time where you shift bits in, you're shifting in the configuration and you can set up the initialization of the RAMs. If you were designing this for an ASIC, and by the way, you do use SystemVerilog for ASICs too, right? Like if you want to tape out, you want to fab a custom chip. But in that case, you wouldn't be able to initialize the RAM because it would come up with random configuration when you power the chip on in a real RAM circuit. You guys with me? What's a real RAM, by the way? It's actually every RAM bit are two inverters pointed to each other. They're cross-coupled inverters that hold a value. But when you power that up, it comes up randomly. Whereas on an FPGA, you have the option of coming up with initial configuration. In order to reset the RAM to that, though, you have to reprogram the FPGA, right? So in other words, once you overwrite the contents in there, then they're gone unless you basically reprogram the whole thing. Okay. Then now we have an assign and an always. So here's an example where we're combining an assign and always. The assign just says read data is mem at address. And the always checks to see it's active on the positive edge of the clock, and it checks if write enable is asserted, and if so, it puts write data into mem address. So what's happening here? Well, it is actually reading and writing potentially. Well, it's always reading. It always reads. So whatever the address is, it's going to spit out the data at that address. So you don't have an option whether you want to read or not. The writing is controlled by this write enable control signal. And the writing is synchronous. The writing requires a clock. The reading, however, doesn't. The reading is asynchronous. So I can read something out of this RAM. I put it without a clock. I just put the address, and then the address will percolate through the RAM, and I'll get the contents of the RAM. So I have an asynchronous read port, or asynchronous read operation, and I optionally can write. And if I write, the write is synchronous. All writes are, I've never seen an asynchronous write. I don't think that's possible. You need a clock to write. The clock is what causes the write to happen, whereas the read can potentially be asynchronous. Right? What does that mean exactly? Well, it means that I can read inside of one clock cycle. In fact, if I wanted to, I could read 10 different entries in that RAM inside of one clock cycle. But if I want to write, I can only do one write per clock cycle based on the description here. Does that make sense? Okay, so what will happen when you synthesize this? Well, the problem is that this is how the register file works on the MIPS processor and the RISC-V processor. However, that RAM that makes that register file is actually constructed differently than a traditional RAM. Most RAMs, if you actually build a RAM, it requires you to have a synchronous read and a synchronous write. But if you have a small RAM for a register file, you can get away with an asynchronous read. You guys with me? Okay. Okay, so if I wanted to have a synchronous read, all I would have to do is move the read logic inside of this always. So that way, the read data is now only going to update on the rising edge of the clock, right? So this way I can do one read per cycle. I could do one write per cycle, but only to the same address. Make sense? Okay. Okay, so let's see. So why don't we, maybe I should actually, instead of just showing this thing, let me do a quick demo here. So let me create this RAM. So I'll create a RAM here, and I'll say module RAM, and I'm just going to put this all in like its own self-contained test bench. So let's create a logic.
When would you want asynchronous or synchronous read?
The only time you're going to use an asynchronous read is a register file or a test bench. Generally, it's not practical in hardware to do asynchronous read. And so what actually happens is, I mentioned earlier that if you build a RAM array, so generally RAMs, SRAMs, static RAMs, there are two inverters pointing at each other, and then there's two additional transistors that are used to activate the cell in there. So generally there's each inverter is 2 transistors, and there's 2 additional ones. So there's 6 transistors per bit in an SRAM array, right? But usually when you have that sort of arrangement, it requires a synchronous read, synchronous write, right? If you want an asynchronous write, generally they actually, the way they do that is they'll actually use flip-flops in an array, and then they'll put a big mux on the output. So the mux will be combinational, and the mux will just control which one of those flip-flops, well, multi-bit flip-flops, one of those, multi-bit flip-flops, which one of the multi-bit flip-flops is routed through the mux, right? The problem with that is that there's a big fan-in. That mux has a big fan-in. There's 32 inputs into that mux, and that's just for a 32 deep. That's not scalable, so you can't make a very big memory array that way because there's too much wire congestion that would be coming into that mux, right? So if you have a register file that's small, you can get away with that, or if it's non-synthesizable, like a test bench. But if it's a real RAM that's deeper than 32 entries, you pretty much have to use an actual RAM, which is a synchronous read, synchronous write. So what would happen though if you tried to make a huge RAM that had an asynchronous read and put it on an FPGA? I've never tried it, but I imagine your clock speed would be horrible. Like it would only run at like 10 megahertz, right? I expect that's what would happen. Okay, so here's a RAM. Maybe we should try that, actually. It might be a good thing to try. I wonder how long it would take to do that. Well, let's come up with a RAM here. So let's make it 7 bits wide, just for instance, and I'll call it mem. Call it whatever you want, and I'll make it 8191 down to 0, and then assign out equals mem, not RAM, mem of address, and then always at pause edge clock. I'll say begin, and if write enable, then mem of address is assigned to data in, and I'll make this data out. And then end. Okay, a couple things to note. Notice I just use always. I didn't use always underscore FF. That's an option. So always is just, if you just say always, that's just the old school way. I probably should say always underscore FF though, because it's kind of protects me a little bit. Compiler knows what I'm trying to do. Notice also I use the non-blocking assignment. What would happen if you use blocking there? I think it would be fine, but I wouldn't want to risk it. I'm using non-blocking because it's synchronous logic. And I need to declare all my stuff. And one thing that's kind of strange about SystemVerilog, I mentioned that SystemVerilog has concurrent semantics, which means that in general you can kind of scramble the lines of code. It won't make any difference. But you still have to declare the signals before you use them. So there's some weird ordering when it comes to declaring signals, even though the lines of code are not supposed to matter. I mean, you should be able to, really, you should be able to declare them after you use them, since the order doesn't matter, right? But it doesn't let you do that. So I'm going to say logic, WE, logic, what's the address? 13 bits? Yeah, 12 down to 0. Address, logic, 7 down to 0, data out, data in, right? And clock. Okay, makes sense? All right. So now I will say vlog ram.sv, compiled, then I'll say vsim ram. And that should bring up model sim. There it is. Okay, now I go into design is being optimized. That can't be good. Okay, yeah. So notice I have no objects here. I got no signals. So I'm going to have to go into simulate, start simulation, work, RAM. I'm already simulating it, but unfortunately I have to apply full visibility to all modules. Hit OK. So I have to restart the simulation, tell it to give me my signals, which it did. They're right here. So then I'm just going to drag those guys in. And now I have to be my own test bench. So actually, you know what? Screw that. I'm going to put my stuff in here. I don't want to do the forces. I'm going to say, I'm going to mix in some test bench code here. Okay, now normally the test bench would be separate from your design and your test, but I'm going to be lazy here and I'm just going to put everything into one module. So I'm going to say always begin end. And this will be my clock. So I'm going to say clock equals 1B0, pause for 5 units, clock equals 1B1, pause for 5 units. That gives me my clock. And then I'm going to set my address to be address, right? So I'm going to say initial address equals 13 binary 0, and I'm going to say always at pause edge clock address equals address plus 1. Okay, so that'll increment the address, and then the data in, I'll just set data in to be a constant for now. Assign data in to be 8 hex EF. There we go. And data out is an output. Okay, good. Makes sense? All right, so now I'll come back down to here, and I'm just going to say vlog. I'm going to re-vlog my RAM. And I'm going to come back over to model sim. And now that Questa, excuse me, I'm going to restart. So you got to do restart after you compile. Restart will reload the new design in. Okay, cool. So now I should just be able to run it. Yeah, there we go. Oh, write enable. Forgot about that one. Let's assign write enable to 1. Okay. Okay, whoop, got to compile it. And now, by the way, you can also compile in Questa. You can also type vlog ram here, ram.sv. Or you can go to compile, or you can go to library over here and go into your work and right-click on RAM and say recompile. Or you can go up here to the compile menu and say compile over here and say RAM and say compile. There's several ways to do it. So I'm going to restart, and so instead of typing restart this time, I'm going to hit this button up here. I don't know if you guys can see that as a restart button. And I'm going to hit the run button. I can hit the run button here, or I can just type run and run. Okay, so you'll notice that the clock is going and data out is dead. Okay, so what's going on there? If I take the memory, you guys see the memory array is actually in my objects window. You can drag that in. But, oh, it's actually filled in. Cool. Okay, so you can see the memory here. Oh, I should not have made it that deep. That was a mistake. Okay, so, yeah. So you can see that what's happening, yeah, I should have not made it that big, but you can see what's happening is because my address is incrementing from 0, and my write enable is 1, and my data in is EF, you can see that the memory array is slowly filling up with EFs. You see that? The reason why it's staggered is because every cycle it adds one more EF and it's incrementing the address. So it's kind of initializing that array by writing all the entries. The problem is that by the time I write EF, yeah, oops, sorry, that was a, hold on, let me change that. Let me go back and change that. Let's make it, let's just make it 8 entries, right? So this is an 8x8 64-bit RAM, and so the address is now only 3 bits, which is 2 down to 0, right? Okay. Okay, so let me recompile and then go back into Questa and restart and rerun. Okay, so now you can see that, let me zoom in a bit here. Zoom, 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 where's zoom? There we go. So you can see that after 8 cycles, I pretty much fill in the whole RAM, right? And the data out is initially a flat line, right? The reason is because remember that the write is synchronous. So it takes a cycle to write. So by the time it writes, because the address is fixed, or the address is going to be the write address and the read address. But by the time it writes, I've already moved on to the next read address, right? So for that reason, the address is just a flat line until the odometer goes back to 0 and the address flips back to 0, right? At which point I start reading EF. Does that make sense? Okay, so, and also if I zoom in here a little bit more, you can see that the writing is corresponding to the rising edge of the clock. So you see where the cursor is? So this EF, so the address is 4. Now, it's technically changing to 5, right? But it's going to use the old address. It's going to see the old address, right? So the address is changing from 4 to 5, but at that moment in time, it sees 4. And so you'll see that address 4, which is here, is going to get written on that rising edge. You guys see that? Make sense? So in this case, it doesn't actually matter that the read is asynchronous, because the write is synchronous. right? So it doesn't, I don't think it would change. Well, let's see, what happens if we make it a, so you'll notice that the read, yeah, this is one difference we'll see. You see that the address, when the address rolls back to 0, the EF immediately pops out of the data out, right? If this were a synchronous read, then I would need one whole cycle of that 0 before I'd see the EF. So what'll happen is, if this was the only difference I'd see if this was a synchronous read is that this EF would actually be pushed one cycle to the right. So address 0 wouldn't pop out until the address becomes 1. I'll read address 0, right, at the moment that the address updates to 1, right? Make sense? Okay. All right. Okay, so I show an example of that here. I think this is a 32-bit wide. So you'll notice here, there's this asynchronous on the top, synchronous on the bottom. And you'll notice that the read data, you see how the read data is 4, 5, 6, but when I make it synchronous, the 4 gets shifted over to the right by 1 cycle, right? So by making the read synchronous, it basically delays it by 1 cycle, shifts it to the right, shifts it forward in time by 1 cycle. Okay, so in your CPU, we're going to just give you the code for the register file. And this is it. The register file is going to look like this. It's going to have 2 ports that can just read and 1 port that can just write. And this is intended to match up to the assembly language. The assembly language has 2 operands, right? 2 register inputs and 1 register output. 2 operands and 1 destination, right? And so the register file hardware is designed around that. That's why we have 3 ports. The read addresses, the read ports are asynchronous. The write port is synchronous. And there's no reset signal. You can't reset this thing. You can initialize it on the FPGA, but you can't like clear the whole thing with 1 signal like you can a flip-flop, right? There's no clear. All you can do is, you know, go through every address, overwrite each address. So this is just a pinout. The memory is declared there. It's 32 by 32. I use assign statements for the read address, the read data 1, read data 2, and there's a always FF for the write. Now there is a couple caveats here. There's a couple details. The first is that the address 0, register 0, is always 0. And you guys remember that from 212? That was the same in MIPS too, right? MIPS, RISC-V, ARM, I think ARM has it in the 64-bit ARM does that. This 32-bit ARM didn't do that. In fact, I think in the 32-bit ARM, the program counter was register 0. Anyway, register 0 is a constant 0. So how do you implement that in Verilog? There's a few ways you can do it. I think the version of this that we give you in the skeleton actually does it a different way. The way I do it is I handle that in the read port. So I use a trinary statement. I say, if read address is 0, then just spit out 0. And that's done on both ports. Notice that these ports are kind of copy and pasted because both read ports do the same thing. The only difference is you have to change the 1. You know, there's read data 1 and read address 1, read data 2, read address 2, right? So these are kind of the same thing. But they both access the same mem, right? So they're both 2 ports, but they're accessing the same memory array. So if the read address is 0, then I'm just going to say 0, right? Now there's another problem though, is that remember that when I showed you that example here, actually, this is a bad example because I'm always, well, actually, you know, I think we can work with this. So notice how the address is 7. The address is 7, and I'm working on writing 7. The address is 7, the write enable is high, and the data is fixed at EF, right? But notice that even though in this cycle, I'm writing 7, the data coming out is still red, is still dead, right? So basically what that means in terms of the register file is if I'm writing a register and I try to read it at the same time, I'm not going to read the new value. Because by the time the new value gets written in the register array, I've already given up trying to read it, right? Like basically, if I try to write register 7 and read register 7 at the same time, I'm going to be seeing the old value of register 7. The new value of register 7 isn't going to get there until the end of the cycle, right? At which point it's too late. You guys with me on that? The way to work around that is to create a bypass. So this register file in the slide has a little trick. There's a little trick here. So this is using a nested ternary statement. So the first part of the ternary says, if the read address is 0, otherwise, if it is 0, spit out 0. Otherwise, if the read address 1 equals the write address and the write enable is high. So in other words, I got the read address and the write address match and I'm writing. That means I have I don't want to say a conflict, but I'm reading and writing the same thing at the same time. I am going to, instead of reading the mem array, I'm going to bypass the mem array. I'm just going to say, look, I'm just going to take the write data and spit that back out at you. So if you try to write to the same register that you're reading, I'm going to take the data you're writing and just turn it right back around at you, right? That way, if you read and write at the same time, you'll get the updated value that you're reading, right? You might say, well, why is that important? Because if I write a RISC program and I have an instruction that has the same register for the destination and the source, then I expect the old value of the register, right? I expect to get the old value, right? Because I'm not going to write the new value until that instruction is done, right? You guys follow me on this, right? So if I have like add x1, x2, x3, or and then I say, well, let's see, let me actually, do I want to do this in 2 instructions? Yeah. And then let's say add x1, x1, x2, right? So this x1 will get sent down to that instruction, right? But this is not going to be reflected here, right? 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 I expect the old value of x1, right, when I do that, right? Well, the problem is that we're building a pipelined MIPS processor. And in the pipeline, this instruction is going to be writing the register, while this instruction is going to be reading or it's going to be in the execute stage. Right? The earlier instruction is going to be at the part of the pipeline where you're actually writing the register, and the later instruction is going to be in the earlier part reading the register. Now you might say, wait a minute, I thought you read the register and the decode. Yes, but we're only making a 3-stage pipeline, and I'll talk more about that in a minute. The problem is because we're making a pipeline processor, we now have this problem where when you read and write the same register at the same time, it's not from the same instruction, it's from 2 different instructions that are on 2 different locations in your code. Does it make sense? So you want to actually have this bypass for that reason. You guys following that? Okay, so that's all built into the code, and we're just going to give that to you. The code for the register file is in the project skeleton. My TA wrote it though. I think he did it. I mean, it's the same. It works the same way. I think he wrote it slightly differently, but it has the same functionality.
What is the bypass again?
So the bypass basically says that.
I know what part of the code is it?
What part? Oh, it's the trinary statement. It's so I have it as part of the read logic, right? I think that's actually the only way to do it. That's the only way to do the bypass is the read logic. I think the way Charles did the 0 register was he put the 0 register in the write logic. He basically initialized register to 0, 0, and then he put something in here that said you're not allowed to write to register 0, and if you try, I won't do it. But the way I do it is I say, if you read from register 0, I'm going to give you 0. But the bypass, I think you have to put that in the read logic, and that just says, If the read address and the write address match and you're actively writing, that means that you've got this, you have to activate the bypass. And the way you do it is you have this evaluate to write data. So write data then gets put into read data 1, right? But if this condition is false, if this condition is false and this condition is false, then the fallback is this like else part, which says read the RAM array. Whatever's in the RAM array at address, put that out, right? That's the default, the fallback. Okay. Okay, everyone okay on that? So that's the register file. The ALU, we're also going to give you the ALU. So your job is going to be essentially to build the control unit and to connect everything together, right? So it works. So the ALU is a combinational logic circuit that takes two 32-bit inputs as well as a 4-bit opcode, operation code, and spits out a 32-bit result and a zero flag, a single-bit zero flag. So 4 bits gives you 16 different operations. How many operations do we actually have? There's only actually 13 operations because some of the opcodes do the same thing, like these two. Actually, all three of these. All three of these guys are the same thing, right? So the operations are A and or XOR. There's three bitwise logical operations. Then we've got add and subtract. And then we have 3 multiply instructions. One of them will give you the lower 32 bits of the product, one of them, and then the other 2 give the upper 32 bits of the product. But that depends on whether it was a signed or an unsigned multiply. Right? So we've assigned basically mol h u and mol h, right? Just like in RISC, obviously matches up to the RISC instruction. Then we've got shift left, shift right, arithmetic shift right. This one, both of these do this. Both of these codes do arithmetic shift right. You guys remember arithmetic shift and sign bits. And then we have these guys that test to see if A is less than B. And the output of that is just a 1 or 0, right? In 32 bits, which is wasteful because you're just putting a 1 or 0 out, but you're padding it with 31 0 bits, right? Okay? Any questions about that? So why do we have these? Well, there are a set less than instruction. Set on less than? Set, SLT, set less than. There's a set less than instruction that does this. But also, we're going to use these to resolve branches. The branch of less than. You might say, what about branch of equal? Well, if it's a branch of equal, you would subtract the 2 inputs. And if the result is 0, they're equal. And that's why you have this 0 flag. So there's a 0 flag that comes out that will be high if the result is 0. So that's basically an equal indicator. Assuming, of course, you told it to subtract. You told the ALU to subtract. You might say, well, then what about greater than? Greater than. I think in greater than, you just have to switch A and B and do less than, right? You might say, well, wait, what about greater than or equal to then? Well, greater than or equal to is the complement of less than. So pretty much you just do a less than and you invert the output, right? Make sense? So you can do all your comparisons with just less than and do subtract, right? Now notice, there's a signed and an unsigned less than too. Because that matters, right? Because if, if the most significant bit is set on an unsigned, that's a big number, right? But if it's a signed number, that's a small number, right? So there's a signed and an unsigned comparison. Okay, so this is actually, I think, the same ALU design that's in the skeleton. This one is implemented with a big nested ternary. Did I say trinary? Ternary statement. Nested ternary, which makes like a big if then else. And so it's an assign statement. So there's a few things here. Obviously, these are 2 columns. So this should be fairly obvious. The one thing that's weird is notice that I had to use this typecast because in Verilog, apparently, if you declare a signal as logic and use a less than operation on it, it's treated as unsigned. So if you want to do a signed comparison, you need to use this weird typecast in Verilog, right? The same thing goes for the multiply, but we handled that over here. So over here, we assigned mol HS and mol HLS to be the signed A times B. So we use the multiply operator and the typecast to do a signed multiply. And then we assign that to a 64-bit value that was the concatenation of these two 32-bit values, mol HS and mol LS. Right? Make sense? This is probably a bad way to do it because I think the whole reason why RISC has a mol H and a mol instruction is because in the hardware, they don't actually want to do a whole 64-bit multiply, right? It's meant to save hardware. But yet in our hardware, we actually do a full 64-bit multiply, and then we just store the output, the upper and lower parts separately, right? So this is kind of inefficient. There's probably a better way to do it, but I mean, our intent is just to match the instruction set, so it's not a big deal. But I'm sure there's a more efficient way we can, use less gates for this, less resource. On the other hand, I think it's just use a DSP on the FPGA, but I don't know how big the DSPs are. DSP is a hardware multiplier, transistorized multiplier. Okay, anything else to note here? The shamped is B, 4 down to 0. So the shift amount is B if you do a if you do a the shift amount comes in as B. So the shift amount is specified as shift amount here, and it comes from B bits 5 down to 0. Obviously, the shift amount only needs 5 bits because if you shift more than 31 bits, you just shift the value away. Any questions about that? So, you just have to kind of have an understanding how that works, but we'll have that in your project skeleton. Okay, so in lab 3 then, our objective is to design a pipeline processor that can execute enough RISC-V instructions to get by. In that case, it's, I forget how many. 1, 2, 3, 4, 5, 6, 9, 10, 11, 12, 13, 14, 15, 23 instructions. It turns out that this is a pretty good set of instructions. There's only 23, but if you cross-compile a program from C into RISC-V, it's pretty much going to just be these instructions. I mean, there's a chance you'll get another instruction, but I don't think I've ever seen that happen. At least not in the MIPS case. We used to do this in MIPS. I would have a student that didn't want to write any MIPS assembly. So he just would use a compiler. He'd write his code in C and he'd compile it, or he'd compile it to assembly language, and he just used the assembly language. And we had enough instructions that GCC wasn't generating instructions that we didn't support, right? So this is a decent, nice core set of instructions. Obviously there's more than this, but these are the main ones. Okay, so there's a couple here you might be wondering about though. LUI, you guys know what LUI does? That stands for load upper immediate. So that allows you to take an immediate value and put it in the upper part of a register, right? An immediate is just a number that you put inside the instruction. This one is the weirdest one, CSRRW. This is a real RISC-V instruction, and it stands for Control Status Register Read Write. This is what we're going to use to access these switches and the hex displays on the board. This is our I/O instruction. Guys with me? Okay. Okay, so RISC-V, this is probably going to be new to you guys because you guys are familiar with MIPS and the way that MIPS instructions are encoded into binary, machine code, right? When I presented RISC-V to you, in the first part of the semester, everyone was fine with that because it was almost the same as MIPS. However, the encoding formats are quite a bit different. So when it comes to the machine code part, this is where things get a little strange if you're coming from this from MIPS. So there is an R-type, I-type, and a U-type. For now, there's more types. There's 6 main types, 6 main integer types. Remember, MIPS only had 3, right? R-type is just like the R-type in MIPS, except it's formatted differently. You guys remember MIPS? Remember you had the opcode first, and the function code was last, right? Now, the function code is first, and the opcode is last. And remember, with MIPS, they were both 6 bits. Now they're 7 bits, both of them. Make sense? I don't know why they changed that, right? Also, there's another function code in the middle of the instruction called funct3. So in total, you've got 7 function bits here, 3 function bits here, and opcode here. What's the difference between the opcode and the function bits? I mean, really, all of them are just saying, all of those things are used for the same thing. They're a code to tell the CPU what instruction it is, right? Essentially, right? They all do the same thing, but they're called, some of them are called function bits, some are called opcode. I don't know why. They're all function bits, or they're all opcode bits, right? So unfortunately, this encoding format is confusing, and I used to have the MIPS one memorized, but I never memorized the RISC-V. It's just too many weird fields in there. Also, the registers are 5 bits each, but they're in weird locations, right? Our destination's 11 down to 7, RS2, well, first of all, it's called RS1 and RS2. You guys remember MIPS had RT? RS and RT. Now there's no RT. It's just RS1, register source 1, register source 2, register destination. It makes much more sense that way, right? But they're in random positions in the encoding. Make sense? So you just have to look that up, because unless you can remember that encoding. Also, what's missing? Isn't there a missing field here? You guys remember there was another field in MIPS, R-type. I don't know if you remember that one. The R-type field in MIPS had a shift amount field. Remember that one? Had a 5-bit shift amount. There's no shift amount in this. So how's it doing shift instructions? It uses the immediate, yeah. So remember I mentioned that there was a shift and shift immediate? Actually, I didn't. Maybe I might have mentioned that, maybe not. Are they in there? Yeah, notice that there's shift left logical immediate, and there's shift left logical. In MIPS, if you did a shift left logical, the shift amount was an immediate. It was put in the register, the instruction. If you wanted to take the shift amount from a register, you had to use the shift left logical variable instruction in MIPS. You probably never used that though, but it was there. In RISC-V, they switched it around. So the regular shift instruction pulls the shift amount from a register, and the shift immediate takes it from their instruction, but now it's not the R-type instruction anymore, it's the I-type instruction, so it comes from the I field, the immediate field. Which, when you think about it, that makes more sense than the way that MIPS did it, I think. Okay, so that's the, so let's talk about the I-type. So the I-type is here. Notice that the RS1 is lined up with the RS1 on the R-type, so that makes sense. The function 3 is lined up, the opcode is lined up, the RD is lined up. But instead of the funct7 and the RS2, those are both replaced by a 12-bit immediate field. Remember in MIPS it was a 16-bit immediate field? Now we just have 12 bits, which limits the range of immediates that you can put into an instruction like an add I, for instance, right? However, we also have the U-type, which has a 20-bit immediate. Right? So that's the load upper immediate uses the U-type. So when you use load upper immediate, you bring in 20 bits, and then you follow that up with another regular load immediate that brings in the other 12. And 20 plus 12 is 32. That's how you get it. That's how you can put an arbitrary 32-bit value into a register. Okay? All right. Yeah, so also, I don't know if you, these are all the instructions that are in that format. These are all the instructions that are in that format. These are the instructions that are in that format. The CSRRW instruction is a weird one, and it actually is in the I type, and I'll talk about that more in a minute here. Okay, actually, I'll talk about it now. So the CSRRW instruction is, as I mentioned, it's a control and status register read and write. And the problem is with it is that it insists, the instruction reads and writes a control and status register at the same time always. So it takes the immediate and it uses the immediate field, the 12-bit immediate, to look up a control register, which is an external register, an I/O, and read that value, right? And it puts the result of that into register RD. So it's going to read a special register that exists outside the CPU core, which in our case is the switches. You know the switches on the board? That's what we're reading, whatever the user has put the switches into. But the problem is that at the same time, it takes whatever's in RS1 in the general purpose register file, and it writes that into the CSRs. Well, we can't write a value into the switches, right? Likewise, we want to be able to write a value into the hex displays, but we can't read the hex displays. There's no way to read. I don't think we can you? No. No, because those pins are outputs only, right? The hex. You guys did the hex decoder, right? So those are outputs. You can't read those. So what are we going to do? Like this instruction says you have to be able to read and write all those control registers. Well, we're just going to hack it and say that if you want to read the hexes, if you want to write the hexes, you write the hexes, there's no read that happens. And if you read the switches, then there's no write that happens. You guys with me on that? It just depends on what you put in as the immediate, what address you put. We're going to give you special fields for that, registers. Okay. Oh, by the way, do I have RARs here? Yes, I do. Java-jar RARs. So we have the special version of RARs that's available on Dropbox. If you go to control and status, up there, my TA Charles modified the code of RARs and he added IO0, IO1, IO2, IO3. These are the IO registers we're going to use in class. And so if you run the special RARs, not the one that's on GitHub, this is our RARs, you can actually use these to define the switches on the board and the hex displays. Now you might say, well, wait a minute, why is there 4 then? I don't know why we have 4, but only 2 of them do anything. I think IO0 is the switches and IO2 is the hexes or something like that. It's in the lab sheet. I'm not sure why we have 4, but those 4 were added. These guys, by the way, are other CSRs that you can access in RARs. Of course, you won't have the support for these in your CPU. But all of these things under control and status are accessed normally through the CSRRW instruction, or CSRRW. Okay. Okay, so the CPU is going to have an instruction memory. And by the way, let me just, one of the issues with this lab, by the way, is there's a huge jump in difficulty from lab 2 to lab 3. Lab 1 and lab 2 were pretty simple. Lab 3 has you designing the whole CPU. We have tried to build it up more incrementally. It never quite worked. We used to have a lab where you just built the fetch stage And that was super confusing because like you're fetching instructions and they're not going anywhere. You know, it's like, then you had to test it with a test bench. And we had a lab where you would just design the ALU. And then we had a lab where you just design a test bench for the ALU. But that was crazy tedious because we used to hide bugs in the ALU and force you guys to find them with a test bench, but it required dozens of test vectors. It was very tedious work. No one liked it. Then we used to have a register file lab, had you design that and test that for the read, you know, the read and write, simultaneous read and writes. That was boring and no one liked it. We used to have a lab where there was only R instructions, but that was really weird because the R instructions don't give you the ability to initialize a register in the code. So we had to initialize the register file with a special init file, and then you had to write code using only R type instructions, which is really hard and frustrating. So we never really found a good way to step up to this lab. So unfortunately, yeah, that's why we give you 3 weeks for this lab, because you're going to have to put a lot into this design as compared to the last two, just to let you know. But we do give you the ALU and the register file, right? So just keep that in mind. The idea is that the CPU is going to get the instructions from a RAM that's a synchronous read RAM. It's actually a ROM because you can't write to it, and it's going to sit next to the CPU. And the hex decoders that you built in Lab 2 will also be in there, because when you do the CSSRW instruction, that's going to push out a 32-bit value outside the CPU. But then we're expecting that 32-bit value is going to be routed through your hex decoders before it goes off the chip, off the FPGA. So that way, when your CPU does a CSRW instruction, it'll update all 8 hex displays at once, and they'll be decoded. So your CPU will put out, for example, hex value, A on 4 bits, and that will go through the hex decoders, and it'll actually show up as A on the FPGA board, right? So we are going to use your code from Lab 2. Okay? Make sense? Okay. Now, you don't have to modularize them like this, though, by the way. You don't have to create a separate... This is not to imply that you have to create a separate... I mean, you already have modules for the decoders, but like you don't have to have a separate module for the instruction memory. You can mix all this into one design. This is the logical organization. In other words, the instructions are stored on chip. You're not going to go off chip for your instructions, which is what real computers do, right? They go out to DRAM, off chip RAM. We're going to store the instructions in on-chip RAM. And it's actually going to be a ROM, because you're going to initialize the instruction memory using an init file. And that's going to get burned into the ROM when you program the FPGA. And then when your CPU starts fetching the instructions, it's going to have the instructions in there. Make sense? Okay. All right, so here is the beginning of the CPU. So, because it's always hard to figure out where to get started on this lab. So you get started with a module called CPU. So we're basically doing kind of a top-down design, right? Start with the CPU, work your way down to the details. So in the CPU, going to declare your instruction RAM, which I have as a 4096 deep, 32-bit wide. That gives you up to 4096 instructions. You can actually make it bigger than that if you want, but your code is going to be like less than 100 instructions, so there's really no reason to, right? So that would give you 4 times 4, 16 kilobits of instruction memory, right? And then the initial statement there is going to allow you to initialize that RAM with a program.rom, which is actually just the code that you can export from RARs. So you write your code in RARs, you export it, and it becomes a hex file, a hexadecimal file, text file. And that hexadecimal text file is already in the right format for SystemVerilog to consume and put in. Just a bunch of 32-bit hex values on one line each. Right? It's just the hex dump from RARs, right? Okay, and then you need a program counter to keep track of where you're executing. You need a signal to hold the instruction, and then this thing is going to control your program counter. So the program counter is going to increment, and you're going to pull out the corresponding instruction from RAM, right? So this is basically your fetch, your instruction fetch and your program counter. And of course, if there's a reset, then you're going to reset the program counter to 0 and set the instruction to 0. The reason you notice that the reset is active low, we've got that tilde there. And the reason is because we're going to get the reset from a button on the board, and the buttons on the board are active low. When you push the button, it sets it to logic 0. So that's why we have that little tilde there, right? So reset is normally high. When it's low, that resets. Okay, that sounds good. Let me know if you have any questions, and we'll get started in the lab on Wednesday and Friday.